Good afternoon, everyone. My name is Nayan Srivastava. Right now, I am pursuing my master degree, that is MSc in Maths, from IIT Patna. Before this, I have done my graduation from Kisan PG College, Bahrain, that is BSc, and mathematics has been a passion of mine, and it guided me throughout my academic journey. In 12th standard, I have scored 92 marks, and further, I have decided to do more in this subject. Today I will discuss matrices. It is a very important part of linear algebra, and today we will discuss how very complex problem we can approach in a very different way and more easier way. How can we tackle that type of things? So let's dive in. First, I would like to start with some basic definitions. So here are some objectives: definition, minor, cofactor, transpose, adjoint, and example. We will discuss these things today. So first, I would like to start with some basic definition. Matrix. A matrix is an m-dimensional array with m rows and n columns in which entries are either real or complex. Usually, representation of matrix is as follows. Yeah. So this is how we represent a matrix, a m cross n matrix with some indexing. That is here the m represent the number of rows and n represent the number of columns. Okay, so this is the general representation of a matrix. So first we will understand some basic notation, that is square matrix. If number of rows and columns are equal, then the matrix known as square matrix. That is if we have m is equal to n, then such type of matrices is known as square matrices. Secondly, rectangular matrices. If the number of rows and columns are not equal, then the matrix is known as rectangular matrices. Okay, so we move forward. Now, the second notation comes order and transpose of a matrix. The number of rows and columns of a matrix is called the order of the matrix. Yeah. The number of rows and columns of a matrix is called the order of the matrix. Here, I have taken one example. Here, matrix A with having number of rows here are 2 and number of columns here are 3. So, the order of the matrix is 2 cross 3. So, by this way, we can represent our order of the matrix. Now, the second definition we are moving forward is the transpose of a matrix. That is, that is the transpose of matrix is a flipped version of the original matrix where the rows and columns are swapped. That is basically if we are taking the matrix A. If we are taking the matrix A, that is the order of the matrix here that we have read previous is 2 cross 3. So the flip version of that, that is the rows are changed into or swapped into the columns, and the columns or you can say or column are swapped into the rows. That is here the rows entries become the column entries. Similarly for the second row, the rows entries become the column entries, and this will become the transpose of the matrix. So in this way we are moving further. So we can only find determinant of the square matrices. Now the determinant of order 1 matrix is the entry itself. Order 1 matrix means if A, we are taking matrix A, order 1 means number of columns and rows are equal to 1. Okay, so we are taking some element A. This is called 1 cross 1 or order 1 matrices. So the determinant of this will be the entry itself, that is A, and the representation of determinant is in this way, that is between mod. You know this is Under this is the mod, but here we are using this as determinant to represent determinant. Okay, now we are moving to define the determinant of order 2 matrix. So here we are taking the general order 2 matrices where we are having 2 rows and 2 columns, and here we are taking general entries, that is we can have any number. Here we can have any real or complex number. That is ABCD can any real number or complex number. So we are defining the determinant of order 2 matrix as here we are using the notation of determinant, and here we are finding that is the multiplying the diagonal entries and then subtracting them. AD minus BC. So in this way we define the determinant of order 2 matrices. Now in determinant. Okay, now we are moving to define the determinant of order 2 matrix. So here we are taking the general order 2 matrices where we are having 2 rows and 2 columns, and here we are taking general entries, that is we can have any number. Here we can have any real or complex number, that is ABCD can any real number or complex number. So we are defining the determinant of order 2 matrix as here we are using the notation of determinant, and here we are finding that is the multiplying the diagonal entries and then subtracting them. AD minus BC. So in this way we define the determinant of order 2 matrices. Now in using the definition of order 2 matrices, how we are finding the order 2 matrix determinant, we can find more order matrices, that is we are going to definition of submatrix. A submatrix is an array after deletion of one or more rows and or one or more columns. That is here what we are doing here. We are deleting one row and we are deleting one column, and the matrix which are left and the entries that are left, and we are forming matrix with that, that is A21, A31, A23, A33. So this is a submatrix of this matrix A. Okay. So now we are moving further. Very important concept here coming, minor and cofactor. What is minor? The minor of a matrix A, that is a matrix a general matrix, is a determinant of the submatrix that is created by removing one or more rows and columns from the original matrix. So I'm telling, what is this? What is happening here? Yeah. So we are learning step by step. The minor of a matrix A, that is we are defining minor corresponding to a matrix. Okay. Any matrix is the determinant. We have learned right now previously, that is what is determinant, okay, of the submatrix. Okay, that is created by removing one or more rows and columns from the original matrix. Now if we are taking this matrix, this is 3 cross 3 means order 3 matrix. How? We have 3 rows and we have 3 columns. Okay, one thing is clear, that the order of the matrix is 3. Now what is the submatrix? The submatrix that is created by removing one or more rows. Now we have to find some matrix corresponding to this entry. ठीक है? Okay, corresponding to this entry means deletion of one row, the element the particular entry in which the particular entry belonging to which row, that row we have to delete, and which column, that we have to delete, and the entries that are left is known as submatrix of that corresponding to that element. Okay, now this is a submatrix corresponding to 1. Now we have to find determinant. So we have studied earlier. We have studied earlier. We have studied earlier. So the determinant of this matrix, what we have seen earlier, that is we have to multiply the diagonal elements and then subtract them. 2 into 2, 4 minus 0. So this determinant of some matrix of A will become a minor entry. Okay, so the minus corresponding to the first entry, that is m, we represented by it m11 is 4. Similarly, we can find for the other entries, and the minor matrix will become this. Now we are moving towards our next definition, cofactor. Okay, cofactor of an element is a matrix A which is obtained when the minor mij, that is a minor corresponding to a particular entry of the element, is multiplied with minus 1 to the power I plus j. Here the indexing ij represent the number of rows and number of columns. Okay, so we have to multiply it with the power of minus 1, that is the sum of their indexes, power of that. Okay, the cofactor of an element is denoted as Cij. If the minor of a matrix is Mij, then the cofactor of the element written as in this way. That is basically the cofactor, that is the cofactor matrices, is coming from the minor matrices. The only difference is this term, minus 1 to the power I plus j. So the matrix formed with the cofactor of the elements of the matrix and is called a cofactor matrix. Now we are moving forward. The next concept is adjoint of the matrix. In the adjoint matrix is to take the transpose of the cofactor matrix. Now it is denoted by adjoint of A. And if we are taking general matrix A, adjoint of A is represented by this way. That is, if we are taking, this is only possible for 2 cross 2 matrices. That is, if we are taking order 2 matrices, we have to find adjoint of A. Then we can only thing to do is that we have to swap the diagonal elements, and the anti-diagonal elements we have to only multiply with minus sign. Then in this simpler way we get the adjoint matrices. Now here are some very important properties of adjoint matrices. Yeah, here we are taking general matrix A with general matrix A of order n. That is, we have number of rows and number of columns are n. Basically n. N can be any integer. Okay. So the first property is A times of adjoint of A is equal to, what is this? Determinant of A. Okay. Multiply with In, where In is the identity matrix of order n, which is equal to adjoint of A into A. Now we are moving towards our second property. If A is a non-singular matrix of order n, then determinant of adjoint of A is equal to determinant of A to the power n minus 1. Okay, maybe you are not familiar with non-singular matrices. So very easy definition of this. Non-singular matrices are those matrices which have non-zero determinant. You know the definition of determinant, I have told you earlier. So the non-singular matrices, square matrices, are the matrices which have non-zero determinant. So we have when we have to find the adjoint matrix, then we have to find a determinant of the matrix. So it is very easier to only calculate the determinant of A, matrix A, with to the power n minus 1, that is the order of the matrix. I will discuss some question regarding this. Have patience. If A, the third property is, if A is non-singular square matrix, then adjoint of A is equal to determinant of A to the power n minus 2 multiply with the matrix A. Now moving towards my fourth property, if A and B are non-singular square matrices of the same order, then adjoint of AB is equal to adjoint of B into adjoint of A. Here we are following the reversal rule. That is, adjoint of AB is equal to it is not equal to adjoint of A into adjoint of B, but it is equal to adjoint of B and adjoint of it. That is, we are reversing the process. So this, in this way, this is known as reversal rule. Now we are moving towards our fifth property. Adjoint of A transpose is equal to adjoint of A to the transpose. Means if we are taking any matrix, transpose matrix, okay, we have to find the adjoint of that matrix. Then it is equal to adjoint of that matrix, means the original matrix. Then we are taking the transpose. Both are different. Okay. Now we are moving towards our sixth property, adjoint of K, where K is any scalar. Then is equal to K to the power n minus 1 into adjoint of A. So now we are moving towards some questions. Maybe you are not getting this, but after doing some question, we will get it. Now, here we are taking one 3 cross 3 order matrix. What we are taking? One 3 cross 3 order matrix. First of all, we have to notice this. Then the next term is the trace of the matrix. Sorry, I have not mentioned the definition of trace, but now I am telling you. Trace of the matrix is the sum of the diagonal entries. This is the diagonal entries of this particular matrix. So, what is trace? Trace of A will be 3 minus 3 plus 1. So, it will equal to 1. So, first we have find trace of the matrix A. Now, trace of the, what we have to find? We don't have, we are not finding here the trace of matrix A. We have to find the trace of the matrix this, adjoint of A. So, now what we have read earlier, the properties, the 6 properties, we have used that thing here. So by the property third, the determinant of the matrix A, here when you will find this is 1, and the order of the matrix is 3. We are using the property third is adjoint of A is determinant of A to the power n minus 2 with times of A. So here determinant of A is 1, the value of n is 3, 3 minus 2 is 1, and multiplying with the original matrix A. So what we get, adjoint of A is equal to A. So basically what we have to find here is the trace of the matrix A. So what we have calculated here is 1. So how much easier is this? So here what is the question is asking you. If A is a square matrix of order 3, means we have 3 rows and 3 columns, such that determinant of A is equal to 5. Okay, then find determinant of adjoint of 4 times of A. Okay, here 4 is a scalar. Okay, now we have learned earlier the properties, the very magic properties of adjoint. So we are using here this. Okay, by property 6, what property 6 are telling you? Adjoint of 4A, where we have earlier we have learned for K times of A. Here the value of K is 4. Okay, so K times of A is equal to K to the power n minus 1 into adjoint of A. That is the property 6. But here we are putting the values. So the value of K is 4. Okay, so K times of means K to the power 3 minus 1. Here the order is 3. So 4 to the power 3 minus 1 times of adjoint of A. First we have to calculate this. So 4 to the power 2 is 16 times of adjoint of A. We have calculated this value. What we have to find? Determinant of this. Okay, so we have taken determinant both sides. But what we are doing here, we are taking the scalar part, that is 16, out of the determinant. So we have to take the power 3. This is a property of matrices. Okay, we have to take power. If we are taking any scalar outside of the determinant, we have to take that power, means that power is equal to that order. Here the order is 3. Okay, 16 to the power 3 times of adjoint of A. We have seen in the properties that how we find determinant of adjoint of A. Here So we are using this. So the determinant of adjoint of A is equal to determinant of A to the power n minus 1. Means here the order is 3. So we are using 3. Now 16 to the power into determinant of A is given already. So 5 to the power 2. Now the answer is 16 to the power 3 into 5 to the power 2. So in this way we have solved such a typical problem. If you have seen how can we find adjoint of adjoint of A is much simpler, but how you find adjoint of 4 times of A. So in this way we have used the properties to solve them. Now I have to discuss some more thing with you, that is to find determinant. This process what I have tell you is simpler, and maybe simpler, what can we say, simpler not, but very calculative. But using the concept of eigenvalues, we can find it in a more easier way. If you know the eigenvalues of the matrices, you simply have to protect them. You simply have to protect them to find a determinant. And if you know the eigenvalues, you have to simply sum them to find the trace of the matrix. Maybe the size of the matrix is 15 cross 15, and you know the eigenvalues. Many concepts are there to find the eigenvalues very easily. By Cayley-Hamilton theorem we can find, but if we have know some properties, some magic properties of the matrices, which maybe you have learned earlier, you can find the eigenvalues very much easier. So in this way I concluded my video, my lecture, and I hope you will all enjoy this. Thank you so much.